Thank you, Marian, for your kind words, and thank you for organizing this event that we really like to be here. Thank you, Eric, too. Today, we are going to present a little bit what we do in our lab. It's a little bit an overview of our capabilities and our services. So you can count on us if you have any issue or or you want to explore better material models for your application. So first of all, Applus Group, it's a multinational company that has many different locations, and one of these locations is Applus DatapointLabs, which it's located in USA, in Ithaca, New York, and we are mainly focused on testing for CAE and material card calibration. So we have been in this business for already 30 years of experience. For sure, I'm not 30 years of experience right now, but my colleagues have been working in the company for more than 25 years. So we have a deep knowledge on material testing, especially on polymers, but also other kind of materials. We have accreditation for ISO and NatCap in terms of aerospace and defense for metallic and non-metallic materials. And we usually test more than 2,000 materials every year. So we have a background of more than 40,000 materials. And our usual turnaround for the testing data, it's just 5 days. So in terms of capabilities, as I said, we test many different material types, from plastics, composites, foam, rubbers, to more fancy and funny stuff like chocolate or some kind of food. We have capabilities to not only characterize materials at room temperature or quasi-static, but also at different range of temperature between cryogenic temperatures to high temperatures with any kind of conditioning that you need for your application. And also we have deep expertise in terms of nonlinear characterization, post-yield behavior, any dynamic situations like drop, crash, impact, fatigue. We do many creeping tests right now, so we cover most of the applications, and not only for mechanical, but also for thermal and rheological testing. As it's written here, we have a global clientele for more than 1,800 companies in 49 countries all over the world. And we are market leaders in providing testing for CAE. So basically what we do in our daily basis are three different things. We have an extensive catalog of tests, which we call test cards. There you can find any kind of characterization that you need. So we test it, we provide the data to you, and you then play around with your own data. But then one of our most successful product is what we call test packs. Test packs were designed for CAE engineers that they have a lot of expertise on CAE, but they don't know about testing, they don't know about materials. So here we provide a pack where not only includes the material card, but also all the testing that needs to be performed before you have this material card. And then we provided the material, the file in the format that it's needed according to your CAE solver, which we are partnered for more than 36 different CAE software. And finally, we have what we call CAE test bench, and this is just the last step before one can be sure that and confident that our material card works, which is validation of the material card. And this can be done in two different ways. We can do it by using the same data that we use to calibrate the material card. But then we have a second way, which we prefer, that is use another new two different tests, usually impact or 3-point bending tests, which we push the material model to the limit, and we can define framework or conditionings in terms of what setting do you need to use in your simulation according to the material model. And why it's important to have tailored material cards and not anything off the shelf or any data that you can find in any test book or on the internet or wherever. So at the end, a tailored material model is essential to guarantee a certain % of accuracy in your application. Because at the end, you are calibrating a material model using data tested, especially with or focusing on your application. So let's say that you find data of any tensile test or whatever, but in your application, the loading case, it's a different one. It's biaxial or shear or whatever. So it's important to have to take this into account. And also, this can reduce the number of physical testing once you have design your part and build your part, and then you need to prove that it works, because all this iterative process can be done on the simulation world. And this is something that for the last conferences that I have assisted, I think it's a common problem for us to trying to convince people and managers that simulation is a powerful tool that can be used more and more. So we can avoid the expensive testing and long tests in terms of component and system and subsystem level. So the first step is to have a really good material model that can be trusted, and this is why it's we cannot escape the testing phase in this part. So for today, I will show you a brief overview of 3 different material classes that we are used to work with. Polymers, foams, and composites. And we choose that one because particularly I think, or I believe it's kind of the complex ones that we have right now. And polymers, it's something that they change a lot depending on the formulation they have, depending on the conditions, depending on the strain rates, even the same material, with the same provider, but manufacturing 2 different plants or 2 different days can give you different results in terms of testing. So they are kind of funny to work with. And foams and composites, as you know, they include many complexities like anisotropy, crack evolution, different failure mechanisms. So they're kind of also funny to So the material models that we are presenting, it's Law 76, which is called SAM, that was developed, if I'm not wrong, by Paul Dubois and his team. At the end, it's a multi-yield surface where you need data from different loading conditions to develop this yield surface that then is used to calculate the proper behavior of the material. Then for foams is the foam tabulated model, which it's kind of similar or based in Fuchang model. And for the composite model, it's Law 25 and Law 125. They are pretty similar to MAT 58 for Dyna. So for this complex material model, which is SAM in terms of polymers, first of all, it's not recommended for reinforced polymers, but this is something that we already are using with reinforced polymers, so we can achieve kind of the process on how to calibrate for reinforced polymers with more or less good success. So we use an iterative process where the optimization it's required. So you start by testing the simple load cases that you have tested, so tensile, compression, shear, and notch. Then you calculate the parameters, check if there is an error between your simulation, and your experimental data, and you iterate again and again and again until you have validated this portion or these simple cases, load cases. Then you move to the more complex conditions, which is usually 3-point bending and impact simulation. And then you adjust what you need according to the results until you have the proper solution. This process is also used while calibrating Gizmo, for instance, or TM or bicewald laws that are complex and are based on not only the material properties, but also it takes into account some numerical parameters that needs to be calibrated. Once this process is done, we give back to our customers our material cards in the right format, so they can just plug and play in their own models. For the foam, the process is kind of more straightforward. So you have a bunch of data directly from the experimental side. In this case, it's strain rate dependent. So we have a bunch of curves. Then what we do is we reduce the noise, reduce the number of points. We extrapolate the data up to usually between 20 and 200 megapascals, depending on the contact surface and so on the rear end. And at the beginning, we extrapolate the tensile. For this particular model, I think we can also introduce a tensile curve, but we usually go this way because the application is more for impact. And then once we have this extrapolated curve, what we do is we filter the first derivative. And this step that was suggested by Marian, it's really the key in order to guarantee the stability of the model. So as you can see, the yellow curve is the first derivative of the curve. You can see a bunch of noise and sharp edges. And then when you do the first derivative, you can filter it, you can smooth it out. And then you integrate this curve again, so you can get the red one, which is kind of almost the same curve of the dotted line. So in this way, we can achieve a good stability for the model, particularly for forms and the large deformation of the elements. And finally, for composites, it's kind of a mix between both. Usually, MAT 58 or low 25, it's pretty straightforward from the data. But then sometimes if you want to include some damage evolution, crack propagation, or delamination, you also need to do some iterations on your process in order to get the right parameters and adjust whatever you need to. And all these iterations is we have developed our own tool, mostly in Python. So it's been integrated for LSDyna and OpenRadioss, so we can run all our simulations through this iterative process and be kind of efficient in this way. So as results, I just said it for polymers, a couple of examples for the impact test and the flexural test. As you can see, we can correlate pretty good the results, even though, as I said, this was a reinforced polymer, which is not recommended for some, but we can do it without any issue. In terms of the poems, sorry, there was the video comparison, but I don't know why it's not working. You can see for the simple test of compression cases and the strain rate, it matched pretty good the experimental data, and for the impact test, it's matched perfectly, both the loading phase and the unloading phase. And finally, in composites, for this project, we validate just the pure modes, 2 tensiles at the different orientations, and then the shear, which was a little bit noisy in terms of simulation, but it worked pretty good also. So a brief summary of these 3 models. So for polymers, as I said, they are strong strain rate dependent, and the damage evolves progressively. So here, what I usually recommend is use as much as DSC as you can, and you can pay. because it's really the key on having a really good set of data that then you can play around and tune your model and learn a lot on that. It's important not only to stick to just tensile or compression and so on. So test as much as you can in terms of notch test, different strain rates, and so on. So we have a really huge amount of data available, and we could avoid guessing what's happening with the polymer after some of the conditions, because this is a big problem when simulating or calibrating models for polymers, that they change the behavior from ductile to brittle, from brittle to ductile really fast. And if you don't have the data available, it's impossible to guess and calibrate a good model that then when you apply to your own applications, you may say this model is not working. And that's because we are missing some of the data. So we didn't calibrate the material card properly. For foams, the main issue or main difficulty or challenge are the light deformation and the disintensification behavior. And here, the important part is the filtering of the derivative, as well as to try to extrapolate the data as smooth as possible, so you can have a good smooth curves. And finally, for composites, strain rate dependency is not that high in this, at least the ones that we have tested. It's important to define which strategy of modeling do you want, if you want to go by ply or more laminate model or any homogenization or whatever. But again, if you have a composite, test it at different orientations, as many as as different conditions as possible again. So that was all for me. Here you have the contact from my colleague and CEO and lab director Brian, also Barbara here and myself. And then here are our websites. It's important. The second one, I think it might be interesting for you. Nomads. It's where we publish all the different conferences, papers, and so on that we do, and all this information is free, so you can take a look and see how we work. Okay, thank you so much.